We've been looking at probability distributions this chapter. And now today we're going to get into a specific type, and it's called the binomial distribution. The binomial distribution satisfies the following conditions. The first condition is there has to be a fixed number of trials. So whatever I'm doing, if I'm flipping a coin, if I'm rolling a die, if I'm drawing cards out of a deck, there has to be a set amount of trials. I'm going to flip the coin 10 times. I'm going to roll the die 100 times. There has to be a fixed amount of trials. How many times are you going to do your experiment? Second condition is each trial can only have 2 outcomes, or outcomes that we can reduce down to 2. So maybe we can make them into 2 different groups. The outcomes are either considered a success or a failure. So again, only 2 outcomes. And kind of the cool part, the reminder for this, we have the binomial distribution. The prefix bi means 2. Bicycle has 2 wheels. Binomial, 2 outcomes. So looking at that prefix bi. The third condition, the outcomes of each trial must be independent of each other. So that means the probability of my first trial happening does not affect the outcome of the second trial or the third trial. So the probability of success for each trial is going to remain the same. And that leads us into, that's the fourth condition. Probability of success must remain the same for each trial. So that's linked to the events being independent. If any of these 4 conditions are not met, the distribution you're working with cannot be considered binomial, and then you're not going to be able to use, we're going to have special formulas and ways to find mean, variance, and standard deviation. So if even one of those is not satisfied, it's not considered a binomial distribution. And in our next section, we will learn about some other types of distributions that then might work for you. The outcomes of a binomial experiment and the corresponding probabilities of these outcomes is considered a binomial distribution. So the outcomes of a binomial experiment, so those conditions have to be satisfied, and then the corresponding probabilities of those outcomes, that's considered a binomial distribution. So all 4 of those conditions met. So you have a binomial experiment, and then we're looking at the corresponding probabilities of those outcomes. And we'll get into some specific examples, and we'll go through and pick out if the conditions are met, and we'll find probabilities and all those things. All right. So let's say we have a coin tossed 4 times, and we want to find the probability of getting exactly 2 heads. We could solve this using a sample space. So we could figure out all the different ways we could get exactly 2 heads, first and second toss, second and third toss, all those different ways. We could do that. Or we could think about, could this be considered a binomial experiment? So take a minute and look at the list of 4 conditions you all just wrote down and see if all 4 of those are satisfied. Just take a minute, think about it. We'll talk about if they're met or not. We'll look at each condition specifically. But I want you to just take a minute, take a little pause here, and see if you think all 4 of those have been met. So let's look at condition 1. Are there a fixed number of trials? Yep, we said we're going to toss the coin 4 times. That's fixed. It's set in stone. Second condition was, are there only 2 outcomes for each trial? There are, either heads or tails. There's nothing else I could possibly get when I flip a coin. So we have 2 outcomes. The outcomes, they're independent. So the outcome of one toss, or even the outcome of just each coin, doesn't affect the outcome of the other tosses or the other coins. Everything is independent. which then leads us into the probability of success. And in this case, we're looking at the number of heads. We want exactly 2 heads. So the probability of getting heads is a half in each case. So for each coin, each toss of that coin, probability is a half. That doesn't change. It stays steady across the board. So can this be considered binomial? Yes. All 4 conditions are met. So now that we've considered the conditions and we found this is a binomial experiment, let's find the probability. So we have a binomial experiment. Now we want to look specifically at finding our probability. So we want exactly 2 heads, and in this case heads is considered our success. That's what we're looking to have happen. And 2 tails, and tails in this case would be considered a failure. The probability of that happening, we want the probability of heads times the probability of heads times probability of tails times probability of tails. Since we want all 4 of those things to happen, that's why we're multiplying. I don't want 1 head or another head. I want 2 heads and I want 2 tails. So the probability piece we're already very familiar with all our work with probability. We're already very familiar with that. Now the piece we have to consider, that'd be great if this is all we had to do. But the part we have to consider though, we have to consider that the 2 heads could occur on the first and second toss, first and third toss. So we have to figure out how many different places the heads could actually land. So we want the number of combinations, 4 things taken 2 at a time. So we want 4 things taken 2 at a time. And that's just the formula for it. If you want to write down the whole formula, I know most of you just go with the calculator shortcut. And so the probability of exactly 2 heads, we take our 1/16 times our 6. That will give us a probability of exactly 2 heads happening. So to help us out a little bit here, instead of having to think about those things separately all the time, okay, so now I gotta find the probability, then I gotta try to do a combination thing. There's a beautiful binomial probability formula for us. Here is our formula. The key here, the probability of exactly so many successes. And that first part of it, guys, the first part of that is just, let me grab a different color here. The first part of this is just the formula for our combination rule. It's just the formula for our combination rule. So if you want to make that little add in there, you can. So just a couple of key things for us to notice. We have the P of S is our probability of success. In our formula, that's just denoted by P. If I know my probability of success, to get the probability of failure, which is denoted by Q, we just do 1 minus P. And also just one other little side note here for you too. Probability of success plus the probability of failure, if you add those 2 together, they need to equal 1. It's a binomial experiment. There's only 2 possible outcomes. So you're either going to have a success or a failure. There's no other choice. So if I add those 2 probabilities together, they need to equal 1. They need to equal 1. Alright, so let's apply this. We have 90% of graduates of State University who apply to a particular medical school are admitted. This year, 6 graduates from State University have applied for admission. Find the probability that only 4 of the 6 will get in. You first of all, and yes, I understand this section is about binomial distribution, so yep, let's just start plugging and chugging in the formula. Remember, we're going to learn about other distributions, and we need to be able to pick out when to use each one. So let's do just a quick rundown of our 4 different conditions that have to be satisfied. Condition 1, fixed number of trials. How many trials do we have? We have 6 trials, that's fixed. Only 2 different outcomes. Do we only have 2 outcomes? Yeah, either they get in or they don't. Are trials independent of each other? So if person 1 gets in, does that affect person 2 getting in? No. So actually, that means our last 2 conditions are actually met. The outcomes are independent, and also the probability of success doesn't change. Each person's probability of success is the same. Doesn't matter if the person before them or after them gets in. So if you consider this to be binomial, we can start using our formula. I like to pick out, I write myself a little list. I know I need n. I know I need capital X. I know I need P. And I know I need Q. I need to pick out those 4 things. Now you might have to look at, I know we just went through all the notation, you might have to take a peek at that for a while until you get used to the notation. N represents to us our total number of trials. And in this case, a trial is the graduate that's applying. So there's 6 of them. The capital X represents the number of successes we would like. We want to know if 4 of them will get in. P is the probability of success. So if we're wanting to know if they get in, success is 90%. So if the probability of success is 90%, probability of a failure is going to be 10%. Keep in mind, guys, P plus Q needs to equal 1. P plus Q needs to equal 1. So we want the probability that 4 of them will be accepted. I just like to use just the combination notation. If you want to write out the whole formula with the factorials and all, you sure can. 6 people, we're going to choose 4 of them to get in. Probability of success. And then how many successes I want, that's my exponent. Probability of failure, and how many of those I want. That'd be my exponent. Go ahead, guys, try out the computation. We should come up with so double check, make sure you can enter that in your calculator. And then I am going to show you how you can use, there's a table in your book we can use. And then there is also a calculator shortcut for it as well. But I want to make sure that you can enter this part in and get that without any type of shortcut.